Hi guys, it's Dr. McDonald again. We're going to finish up chapter 1. Going to start where we left off. Learning objective 1.5.01, structural and functional complementarity. Now we've talked about this, we just haven't given it a name. We're just saying that the anatomy, the way something is built, depends on what you're going to use it for. And again, a hammer has to look like it does in order to hit a nail. If it looks like a screwdriver, well, you really can't use that. But you can't use a hammer to screw in a screw either. So what we're saying is that the way that we're built, every part of our body is designed to perform a specific function. And that's all that this whole concept means. It is something you're going to need to know, guys. So, mark it down. Okay, organizational levels of the human body, and this is what we actually do in A&P 1 and 2. So the atomic level, we're going to actually start that in chapter 2. And we're going to see how atoms come together and make molecules. Molecules come together and they form organelles. Organelles, think of it as little organs. So what your heart and your liver is to your body, then the organs inside the individual cells, those are organelles. And we'll talk all about that in chapter 3. But these organelles will come together, and all the organelles plus the other accessory structures will together form a cell. And just so you know, the cell is the lowest level that we can actually say is alive. Cells together, usually one or more cell types, are going to make a tissue, and that'll be chapter 4. Tissues are going to come together and form organs. Usually 2 or more tissues will form an organ. So in some cases, it's all 4 types of major tissues. These organs are going to work cooperatively together, and the cooperation between them depends, of course, on which organs we're referring to. But if you take the heart, which pumps the blood, you also need the blood vessels that conduct the blood. So together, it's the cardiovascular organ system. There are 11 organ systems in the human body, and we're going to cover all of them in A&P 1 and 2. All the organ systems together make up an organism or a person. I hope that's pretty straightforward, guys. Not a lot to that. Okay, let's... Okay, I lost my place there for a minute, guys. Okay, so let's continue to move on. I just need to minimize that thing. Okay, now let me find my mover. I hate it when this happens. Oh, there it is. Okay, let's go to the next slide. So the chemical level, we're going to be talking about that in chapter 2. Inorganic molecules and organic molecules together are going to make up our organelles. Here you can see a lot of the different organelles inside a cell. Again, we're going to talk more about this and in detail in an upcoming chapter. The tissues are groups of cells that generally perform a certain function. We'll talk about this, of course, in the upcoming chapters, but you can see groups of cells that are arranged in a certain fashion. The organ level, most folks probably are familiar with the fact you have 2 lungs, a heart, a liver, stomach. You've got the small bowel and the colon, the kidneys. I mean, we've got all kinds of organs that do specific jobs. Here are the organ systems. I don't know if you guys can see it. This is a little bit kind of fuzzy. The integumentary system, that's your skin and the structures that are associated with it. The skeletal system, the bones and the joints go with that. The muscular system, predominantly the skeletal muscles, but the others as well. And then there is the nervous system, which is your brain, your spinal cord, and the peripheral nerves. These four organ systems here are what we are going to actually do in A&P1 after we get past the tissues. First thing we do is the skin, the bones, the muscles, and then the nervous system. Starting in A&P2, you do the endocrine system, which produces the hormones, cardiovascular, the heart, the blood, and the blood vessels. Lymphatic system, it's an alternate system that transports fluid, also has a lot to do with the immune system. The digestive system obviously is for the intake and breaking down of food, getting everything we need out of it, and then of course taking the waste material to be disposed of. Let's see, go right over here. The respiratory system, which is basically the lungs and the airways. And then the urinary system, which are going to be our kidneys, the ureters, and the bladder. And then the very last system that we discuss in A&P2 is going to be the reproductive system, male and female. Let me see, guys. Let me see if I can move my little box over. Our definition: group of organs work together, perform major functions, or do physiological needs of the body. And that's pretty straightforward, I think. Okay, continuing on. The organism level, I gotta move again. The organism, that's just the total person. That's you. All of your organ systems together make up you. And again, just another diagram that shows you how all these things go through these different levels. You need to know these different levels. You need to know the organ systems. You need to know their functions. Not really that much, guys. Now this, let me move again over here. This guy, oops, guess I better leave it like that. This guy is a key concept. Now you need to know this. Homeostasis is keeping ourselves in balance. Now a lot of people think that 98.6 degrees Fahrenheit is normal temperature. Well, actually, it's actually more of a range. Anything less than 100 or more than 96 would be in the general range. And our temperature actually increases throughout the day. Starts out at the coldest level and it will actually go up through the day. Same thing with our blood pressure. Things like this change. We are built to exist within a range. Okay, so if this is 32 degrees Fahrenheit, the freezing point of water, and this is 200 degrees Fahrenheit. No, we got to bring it down. Let's bring it down to about 100, 105. That's probably the range that we're going to be ideally suited for. If it goes too cold, we'll die. If it gets too hot, we'll die. But anywhere in that range, it's unrealistic to try to expect our body to maintain an exact value because we've got all kinds of biochemistry going on all the time. We're constantly in the process of change. But while we're doing this change, we want to keep it within those limits. Temperature, air pressure. If you go down into the oceans, the pressure is so intense it'll crush you. You go up on the top of Mount Everest, the air pressure is so low that you'll die because you just can't breathe in enough oxygen to stay alive. The pH, we have to have a certain amount between this, between how alkaline and how acidic. You go down too acidic, you die. You go up too alkaline, you die. So this is what we're talking about with this. Let me move to the next slide because it really gives a good thing. Let's see, let me move me again. I can move me over there. Okay, so what we've got here, guys, they use this little balance beam, seesaw, teeter-totter, whatever you want to call it. So normally we're in balance. It rocks a little bit, but generally not too much. But what happens if something happens, say it's 50 degrees outside and I go out and start working in the yard or whatever, and then the temperature starts to drop, and by the time it gets into the 30s, I am shivering. What's happened? The change in temperature, the temperature has gone down, which means there's a greater difference between my warm interior and the cold exterior. And what's going to happen is, it's kind of like, I don't know if you guys ever noticed, if you go outside in the winter and sit on the cold ground, that ground will actually suck heat out of your body. You'll get very cold. That's why we have to, that's just the way heat is transferred. So what we have to do is, when this happens, we've got to do something to warm up. Generally, what happens is, when the brain gets the information that it's getting cold, it's going to cause you to shiver, because when you shiver, you're actually contracting your muscles very quickly. And not only do muscles cause movement, but they also produce heat. So that's what's happening. It's getting cold, so we're going out of balance. You see over here, we'll just say this is the imbalance. We're down below our temperature range. So what we do is we try to increase the amount of heat in the body, and all we're doing, and to simplify it, is all we're doing is, if we've got an imbalance over here, we push on this side to try to bring it back into balance. And I will tell you something, a lot of healthcare is just exactly that. Something goes out of balance and we push in the opposite direction. We give medications or whatever therapy to try to push in the opposite direction. So as far as the homeostasis, the nervous system is going to be monitoring this. We monitor everything on the outside, temperature, pain, pressure, things like that. We also monitor things on the inside, like our heart rate, the amount of carbon dioxide in our blood, the acidity or alkalinity of our blood. We're measuring this constantly, and we're correcting it to try to keep it on. I don't know if you guys have ever driven a boat, but when you're on the water, I mean, you got currents, you got wakes coming from other boats. You're always constantly doing little corrections, or even a car. When you're driving down the road, you don't usually do this. You usually just do small corrections. And that's a good analogy, I think, for homeostasis. So this guy is super important concept. You really need to get it. I think I got it, well, it just kind of breaks it down. So the sensor, whatever is actually measuring something, heat, cold, blood pressure, whatever, is going to detect this. It's going to send it up through the nervous system to the brain. The brain is going to receive the input. It's going to find out, oh, it's cold outside. This is what I need to do. Or it could be, I'm thirsty. So the brain's going to say, well, let me get this body up and walk over there and get a drink of water. So the control center makes this decision, and then it passes it on to the effector. That could be a muscle, that could be a hormone, and it's going to get it to get us back into that. Now, coming up, we're going to talk about some very important things. Oops, move me again. There's another, and that's actually, I think, there's just shivering. Look at this one too. I've included several images for all of these, so that if you don't get one, maybe the other one will make sense to you. Anyway, negative feedback. So, okay, here I am. I'm out of balance. I push down here. When do I know when to stop? So if I'm cold, I don't want to jump into an oven because then I'll get too hot. Or if I'm hot, I don't want to go into a deep freezer that's at 0 degrees. You see, we need some way of stopping our compensation. So if something is out of whack on this side and I push down, I need to know when to stop pushing. That's what negative feedback is. Most of what we do in our body is going to be negative feedback. So let me see if I can give a good example. I monitor my blood to see how much thyroid hormone I have. If I don't have enough, then I instruct the thyroid gland to release more thyroid hormone. As the levels of thyroid hormone go up, I get to a point where I'm where I need to be, then I cut it off. A good example, and not necessarily a very kind of crude, but it's very good. In the toilet bowls, when the toilet is flushed, the water runs out. And as soon as it runs out, there's either a float or some other device that measures the water level. And it's going to open up and cause water to flow into the tank. But at some point, we want it to stop. We don't want it to overflow the tank and get on our floor. So once it reaches a certain level, it's going to cut off. That's negative feedback. Another good example, if I come home and it's 50 degrees in my house, well, that's a little bit cool for my taste. I'm probably going to set my thermostat up to about 74, and the heat's going to come on, and it's going to stay on until it reaches that temperature. Now, it may overshoot it 1 or a degree or so, but it's going to cut off. That's negative feedback. Something is wrong, so I fix it, and as soon as it gets back to where it needs to be, I stop doing what I'm doing. If I'm going to the grocery store to buy groceries, and I need to stop when I get to the grocery store. I don't need to keep going because then I missed my turn. Okay, here's another concept. Now, there's not a lot that's involved with this. Positive feedback. What happens here is when you do something, instead of cutting it off, you actually increase it. So the best, they've got here blood clotting. The more platelets that stick together to plug your blood vessels so you don't bleed out, the more platelets are going to come. The platelets get stickier and stickier, and they attract more and more. Probably the one that you're going to see most in the test banks is just labor contractions. So mom's going into labor, and here comes a contraction. The uterus is squeezing. It's a muscle, and it does a certain amount of forceful contraction, and then it lets off. Maybe 8 minutes later, it comes, and this contraction is a little bit more forceful, and then it lets off. And instead of 8 minutes, here comes 5 minutes, and it's even more forceful. And this thing, it continues. The more contractions you have, the harder they're going to come, the faster together, or the closer together they're going to come until the baby is born. That's a positive feedback. You need to know those concepts, period. And let me move me again. I really should stay in one place. Let's see if I can find, I don't know. Oh, well, we'll try up there for a minute. Homeostatic imbalance, just what we were saying. When we get out of balance, this is going to cause our risk of disease, both metabolic diseases or even make us more susceptible to infections. This happens a lot with people when you age. Just like you buy a brand new car. 20 years from now, the car's going to be worn out. the parts are going to wear out, and if you have to continually replace them, and you just, at some point you come to the point where the vehicle is just worn out. Well, we wear out. You use your organ systems your whole life, and eventually, as you grow older, they get less effective. Your immune system doesn't work as good. Nothing works as good. That's just part of it. This will allow us different kind of positive feedback, congestive heart failure. So if your heart's not pumping enough blood, and we've tried speeding up the heart rate, and we've tried squeezing harder, then if that still doesn't do it, then the heart's going to get bigger in order to push harder. But here's the thing, bigger is not better. The bigger it gets, the more stiff it gets, so actually it doesn't work as well as it does when it's normal size. Cardiomegaly is never a good thing. So that's one of the things you have when you get into geriatrics, with the aging. Okay, just a little bit about metabolism. I'm sure everybody's heard about it. Metabolism, the easiest definition, it is all of the biochemical reactions going on in your body. That's it. It's everything. Now, metabolism is divided into two. We've got catabolism and anabolism. Catabolism is where we take something big, like a protein, and cut it up into individual amino acids. When we take in protein in our diet, whether it's plant or animal, we're going to have to cut those guys up into individual amino acids in order to absorb them, and also in order to use them to build our own proteins. That's catabolism. Anabolism is where you take small units and combine them to make a bigger unit. That would be like, well, we take those amino acids, they get taken up by the cells use them to make their own proteins. This is a lot like Legos. You can take a bunch of Legos that's already, we just take some loose Legos and put them together. That's anabolism. We can also, after we're finished, say we're done with whatever we're doing, we have to take them apart to store them. That's catabolism. Usually anabolism, when you build things, that requires energy. Catabolism actually releases energy. But we'll talk more about that later on. Okay, guys, we don't have too many more slides. I'm going to try to get through this. Okay, necessary life functions. We're going to be talking about necessary life functions and survival functions. Now, life functions are things that every living thing needs to do in order to fulfill all the requirements of life. Survival functions are what the bare minimum you can get by with just to stay alive. I hope that's kind of distinct in your minds. People get this confused on the exams, so I want you to kind of understand this. Now, here's one. We have to compartmentalize. We have to separate compartments inside our body and the inside of our body from the outside world. We use the skin as a barrier between all the internal components and the outside world. It helps us to stay hydrated. We'll talk more about that when we get to the skin, guys. Now, for the individual cell, we don't have cell walls. We're not plants and we're not bacteria. We have like a membrane around the cells. It's a barrier. It keeps certain things out of the cell. It allows us to maintain, and again, we're going to talk way more about this, but maintaining a boundary between the inside and outside of anything. So we want to have one between the outside world and the inside of us. We want to have one between the inside of our cells and the extracellular space. Movement, contractility. Well, obviously we need our skeletal muscles to move our bodies, but we also have our heart. Our heart moves. He doesn't move around. He squeezes and pumps the blood. The smooth muscle in our GI tract squeezes and pushes the food through our system. So we have to have this in order to fulfill our life functions. Responsiveness. If you stick your hand on a hot stove accidentally, you need to respond to it by pulling it up. We respond to things around us, especially things that we would consider to be noxious. That's that withdrawal reflex. If you walk into a house and you've got a strong odor of ammonia or whatever, you're going to back off because that ammonia is not good for you. It's toxic. You don't want to breathe it in. That's more like an automatic reflex. We'll talk about that in the nervous system. Here's one. Control the breathing rate. How fast do I breathe? It depends on what I'm doing. I don't need to breathe 25 times a minute sitting here talking to you guys. Now, if I go outside and start pushing a lawnmower, then yeah. Or if I go jogging or something like that, I'm going to need more oxygen. I have to breathe faster. That's my responsiveness. When something changes, whatever it is, I can respond to it. And either, and this is something you see with even single-cell animals. They'll move toward food and they'll move away from things that are toxic to them. Digestion, breaking down our food, putting them into the very simple subunits that we can actually process and use. Metabolism, we've already talked about that. We have to do our body chemistry. If you have no body chemistry, that is a good definition of being dead. Excretion, we have to get rid of waste materials. Carbon dioxide builds up in our blood is a bad thing. You can die from this. Urea, the byproduct of a lot of our metabolism, is toxic. It starts out as ammonia. It needs to be ridded. So we have to get rid of things that we have no use for, especially since a lot of these things are toxic to us. Uremia is something you don't really see a lot about today because we have dialysis, but it's a very nasty way to die. Reproduction, for a life function, yes. There's two kinds of reproduction. We need to be able to replace our cells, not only replace them, but sometimes add more to them. We add more to them, that's going to be the growth, which we'll talk about in a second. But for example, the outer layer of our skin is replaced completely once every 30 days. The inner layer of our stomach is replaced once a week. So we have to continually reproduce those cells to replace the ones that are damaged or no longer functional. And then, of course, the one that most people would probably think of, having children, offspring. Growth is when we get a larger size of an organ or of the entire body. Working out, pumping iron, get your muscles bigger. That's growth. As you grow from an infant to a child to an adolescent and on, that's growth of the organism, the whole person. Okay, guys. Survival needs now. These are what you need to be alive. They are not going to include a lot of those other things. Nutrients. We got to have food, carbs, predominantly for energy. We also have to have those nutrients that we need to make cells. We need amino acids and so forth. So carbohydrates, we need fats, we need proteins, and then our vitamins and minerals. We have to have this merely to stay alive. Oxygen, we have to have air. We need oxygen because we use oxygen to make the fuel that we run on. We take blood sugar and we break it down and we use it to make a fuel. It's just similar to the way that the oil companies get crude oil out of the ground. You can't put that in your car and run on it, but they will refine it and they will modify it and change it, and it becomes gasoline. So we have to change our carbohydrates and other things into this ATP, which is the fuel that we run on. You have to do that with oxygen. If you don't have oxygen, you can make a little ATP, but not enough to live on. Otherwise, people wouldn't drown. Water, we got to have water. We got to be hydrated. All the biochemistry is wet chemistry. It all takes place in water. So we have to have a certain amount of water in our body at all times. If we don't, we're going to die. You get dehydrated, you die. Normal body temperature, we have to stay within that range. I'm sure everyone has fried an egg or so seen it done anyway. You take that egg and you heat it up and those proteins change, and there's no saying you cannot unscramble an egg. So some of the things that keep us alive are proteins, and if the temperature goes too high or too low, they stop working. Remember what I said, if your chemical reactions stop, that's a good definition of being dead. Hyperthermia and hypothermia. And this one may be one that you might kind of scratch your head. We got to have the right atmospheric pressure. We kind of talked about this. If I've been up to Yellowstone and the Grand Canyon, and it's 10,000, 11,000 feet up in the air above sea level, and it's a lot different breathing there, especially if you're coming from a place like around here. We've got 1,000 to 1,500 feet above sea level. It is considerably more. The oxygen is considerably less. There's less pressure. And even though we won't get to this to AMP2, take my word for it, there's not enough. I told you about Mount Everest. If you're on top of Mount Everest, most of the people who die there don't die from the cold. They die from oxygen deprivation, anoxia. They die because no matter how deep you breathe or how fast you breathe, you can't supply enough oxygen to keep yourself going. So just like we talked about with the ATP production, you just run out of ATP. And so you don't have any fuel, you stop, just like your car would if it ran out of gas. I think this is the last one, guys. Yep, we come all the way back around. Well, that concludes chapter 1. I'll be getting chapter 2 up for you guys. This will take us through the first week of classes. You need to watch this. You need to pay attention to what I emphasize, but you need to know what I've got in here. Anyway, thanks, guys. I appreciate it, and I will see you all in just a little while.